So our next presenter is Tom Caputi. So you might be familiar with Tom for his work on ZFS at rest, encryption at rest for ZFS. Today, though, Tom is going to talk about something different. It's going to be related to debugging on Linux. So please welcome Tom.
Thank you. How's that? Can everybody hear me? Nope. Okay, let's try. Is that better? Okay. Hi everybody. I'm Tom Caputi, and I'm here to talk about ZFS debugging techniques. I'm sorry. I was out really late, and between the time zones and eating pretty much only junk food, I'm sorry. Just stay with me, and we'll all get through this, okay? Anyway, I'm here to talk about ZFS debugging techniques, and I've been spending a lot of time over the past 6 months to a year or so just doing a bunch of debugging. So I don't know. Let's just get into it, okay? So here I have a system. I created a pool. Here, let me try to make sure that this is going to be in the right spot. There we go. So I have a pool that I created. And if I do z pool status, there it is. Hooray! And I don't know. Let's start by making a data set. Should be pretty easy, right? ZFS create pool/test. Crap. So this is a problem. People should be able to make data sets. Last time I checked. So I guess the first thing that I'd try to do when I hit something like this is that's amazing right there. That worked, okay? Usually when I break ZFS, or most of the people in this room break ZFS, you can't Control-C it. If you are able to Control-C the process, what that basically means is that your process is busted in Userspace somewhere, for the most part. And that means that this is probably a lot easier to debug than anything else that could possibly happen. So let's try this, okay? I have tmux loaded up here, so let's go back to this. Let's try this again. And since obviously this is a reproducible problem, let's go over here and let's just run htop, okay? This is one of the first things I do whenever I encounter a problem, and you'll notice nothing's happening. Let's search around for the ZFS process and see if it is. Okay, so there it is, and it's asleep. It's not doing anything. It's not really using a whole lot of memory, but this is good. This is all information, and we know that we can Control-C it. So let's quickly do this one other thing. Let's try this one other thing. Go back to the original window. And I'm sorry if I cut out in and out a lot. I'm trying to keep my face as close to this microphone as possible, but it's kind of over here. And let's strace this process. How many of you are familiar with strace? Oh, thank God. This is a wonderful tool whenever you're debugging anything because it will at least tell you usually where the problem that you're trying to debug started, because it will tell you the system call that it's stuck on trying to execute. So let's try this. Let's do strace, and you see it did a whole bunch of nonsense, getting all kinds of things from about what kind of features the pool supports and all these other things. But that last one's weird. Okay, so it's asleep. So let's start with that, shall we? That sounds like a good place to start. Let's go into the code, and let me bring this over. And I apologize. This is a little bit of back and forth. Go over here, and then here. Let me just switch to It'll be easier if I just do it like this. Sorry. Duplicate. Okay. Hopefully that should be easier. But anyway, so let's open up ZFS main.c and take a look at what's going on here. So we know that the thing didn't really the program didn't really call anything before it got to that sleep. It just basically loaded a bunch of other info about the features, but it didn't really get to any of the code. So let's take a look. Just start at ZFS main.c and try to follow it around and see what might be the problem here. So we're going to go to CMD. We're going to go to ZFS, because that's the command we ran, and ZFS main.c. And let's open over here. And let's search for ZFS do create. Pretty easy. Look around, we find it. Let's see if there's anything suspicious here. Dear future Tom, I know how much you love fixing bugs in ZFS. I also know your birthday is coming up in 5 months. That's not even accurate. So I wanted to give you an early birthday present. I added even more bugs to ZFS. I didn't think it was possible to add more. I'm the best. Pass, Tom. Great. Okay, so we have some things here that we need to fix. Let's get rid of this one, because this one's obviously a problem. Let's get rid of this, and we'll go back over here, and this is now a problem, because that's how screen resolutions work. Can everybody see that okay? Okay, so let's do this. We'll quickly rebuild the code. We'll do just make -j7, make install. And while that's happening, let's talk a little bit about if my menu existed. Let's talk about Userspace lockups. So this was kind of the first problem that we just saw here. We saw that everything, the whole process was kind of stuck in Userspace, but we were able to get out of it just by hitting Control-C, which was probably the first thing that you'd try as somebody who's familiar with a Unix system. Like, that's probably one of the first things you'd try, but that's actually a really valuable piece of debugging information, is whether or not you can cancel it. After you've determined this, you can use processes like top, htop, depending on what your preference is, psaux, which can give you the same information but more as like a snapshot, and you can check some really basic things. Here, we saw that the process was not stuck in D, which means that it's not stuck in the kernel. It was stuck in S, which is a sleep state, which basically means that it's cancelable whenever we want to. It's also important to keep in mind that the process might just be slow. It might be doing its job, but it might just be taking a lot longer than you expect. If that's the case, then you have more work to do. But for right now, we've gotten to something pretty easy. So let's go back here. It's rebuilt. Let's try this again. Let's do ZFS create pool/test. Ah, crap. So this is what a crash looks like. Pretty obvious. I'm sure most of you have seen this kind of thing before. And usually, if you're using a UI, you will see this message. Otherwise, you will just see this message, which is very helpful and tells you almost nothing. Segmentation fault, core dumped. And it's kind of a lie, because if you look around, this one is here from before, so ignore that. But, after you remove it, there's no file there. RM does still work. So you run this, it seg faults, and let's take a look at how you debug this. This is also pretty easy to debug, and the reason that this is kind of easy to debug is because there's all kinds of tools and stuff that have existed for, since the beginning of time to help you figure out how to debug this stuff. So let's use the biggest one right now. The biggest one is obviously GDB. So let's get rid of this message if I can. Or maybe it's just there forever. Yeah, it is, but it's not letting me Alt-Tab to it. So here, go away. There we go. Okay, so there now should be a core file here. And there's not. And the reason, I'm sorry, I brought this up before, but usually when you crash a program, it will tell you that the core is dumped, and that is a lie. What you need to do first is you need to set ulimit-c unlimited. What this does is it allows your operating system Linux in this case, and this is kind of a Linuxism. I'm not exactly sure how this works on FreeBSD or any other platform, but on Linux at least, you need to set this in order for it to be able to generate a core file. And a core file is one of the most useful tools that you have when trying to debug things like crashes. So now that we've done this, it will actually create a core file when we do this. And if we do ls core, there it finally is. You know, for real this time, unlike before, which was just a figment of your imagination. And now we can use GDB to solve it. And what you'd normally type is GDB ZFS, which is the name of the binary that you're trying to work on, and then core, which is the name of the core file. What the core file represents is basically the state of your system at the moment that it crashed. So by doing this, you can see right here that here's the stack trace of exactly where it crashed, conveniently with line numbers. Now, we can see that right here, the top of it is this nice, convenient crash the program function, which might have something to do with the problem. Let's take a look at that. So if I just search around here for crash Yep, there it is. And it says this will crash the application. Wonderful. Wonder what it does. This function serves two purposes. First, it crashes the program. Second, it crashes the program. It's worth repeating for emphasis. Okay, that's not good. Here, let's just get rid of this. Okay, so now we've gotten rid of this, and hopefully now we should be able to create a data set and move on to, you know, the actual kind of hard stuff to debug. So let's quickly get out of this. We found this one. We'll do again make-j7, and I can just hit up if I know what I'm doing. There we go. And so this brings us to the second kind of thing that can happen when you're debugging issues. This one's a lot more common. This is a user space crash. Usually when you find a problem, it won't just be that somebody put a sleep somewhere, because most of the time people don't want their programs to just go to sleep. Most of the times they want them to do stuff. So crashes are way more common in, you know, programming in general, and they are pretty easily identifiable by the messages that come out when that happens. Oops, and this is the wrong slide. And I deleted the right slide. So anyway, but basically the system will crash when the system crashes. The operating system will tell you that it crashed. It will usually say something it will usually say it was killed with a SIGINT or a SIGABORT or some other kind of signal like that that you did not issue it, and it will you know, if you have ulimit-c set, it will dump out the core file and allow you to debug it with GDB. Let's go back to this, and okay, let's try this one more time. I have a good feeling about this, and still nothing. But this is something different. So now this time, we've tried to Control-C the program, and it hasn't returned. This is more often than not what I usually see whenever I'm debugging ZFS stuff, because most of the stuff that I, and I'm sure a lot of people here, work with, you know, we write code for the Linux kernel or for the BSD kernel or for, you know, any other kernel that there is. And usually when the kernel crashes, there's not a lot you can do. As soon as I see this, the first thing that I do is I go to dmessage. So I come over here, type dmessage, and very helpfully, ZFS has the stack trace right here. I can see that I don't really understand what this is, but I'm sure we can figure that out if we go to the thing. We called SPL panic, and here, if you look, this is what a standard ZFS kind of assert looks like. So for any of you who are maybe watching on the live stream, or for those of you who, you know, who are more users of ZFS and you see these kinds of messages, I'm sure the developers have seen these all the time, but, you know, when you see a message like this from dmessage that says verify and then some statement, it usually is indicating that that statement is false. In this case, it's saying that whatever the current time is minus some start time is greater than or equal to 5 minutes. And right now we're saying that no time has passed. So that's weird, but I also don't know what would be doing this. But conveniently, it gives us a line number again. So again, this is a really, whenever you're creating an issue report for ZFS developers, this is a very important thing to include, is not just the stack trace, because a lot of times this is what ends up in the issue report, but this is the important stuff. So Let's go take a look at that. This is in ZFS IOCTL.c, and it's line 3349, it says. So we'll come over here, and we'll go to line 3349. And it says, ZFS allows us to create too many data sets, and I misspelled two. We should make sure that we don't create more than a data set every 5 minutes. And then right here it says, in debug mode, you can create data sets every hour. This will give you an excuse to go get some lunch. At least it was thoughtful. That's good. Okay, so anyway, so now let's get rid of this. We found this problem. We know that this probably isn't actually, this isn't actually true. So in this case, we can just remove it. But normally, you would want to very much consider why those asserts were added and, for what reason. Because usually, when somebody puts those in, it means that you will break some piece of code somewhere else very, very badly and in a way that will be very, very hard to find. But let's take this and get rid of it for right now. And now, interestingly, we have crashed the kernel. So the only way to actually get back to a state where we can retest this is we have to restart the whole thing. I have this kind of set up so that basically I go back to a snapshot of the VM every time. But whenever you hit a kernel space crash or anything like that, you do need to reboot and apologize to your local cloud or syseng team. While we're waiting for that to reboot, let's talk about oh, there was Userspace crashes. It just moved a slide down. Let's talk about kernel crashes. The processes basically appear to be stuck, and they cannot be terminated with Control-C. If you look at them in PSAUX or HTOP or anything like that, they'll be stuck in the D state, and usually they may or may not say just the word killed if you're using a bash shell. The reason that they say killed is because literally, if you cause a real problem that actually causes the kernel to crash, the kernel that is how the kernel is built to handle it. Is it literally just sends a kill to the process and kind of hangs it there forever. In ZFS, it's a little. We have some debugging stuff for the asserts that's a little bit nicer, and basically we just hang the process forever ourselves, quote, for inspection. That's what it says in the comment. Whenever you hit a problem like this, just remember that the most important thing that you can report to developers and for yourself if you're trying to debug these issues is to look in dmessage. Depending on how the thing crashed and what kind of other problems may have arisen, the system may have become completely unresponsive, and you might really just be stuck. Let's come back here. So we rebooted the VM, and now I'm going to come over here and paste in just a quick thing. Let's just rebuild this pool real quick and rebuild the code. Does anybody have any questions on this stuff while this is rebuilding? Okay. I'm assuming most of you have probably seen a lot of stuff like this, and because this is the ZFS Developer Summit, so I kind of assume that that's kind of the basic stuff. So let's look at something a little bit different. After we create our data set, sorry. This screen is a bit more cramped than when I did it in rehearsal, so I apologize. So let's create this data set. ZFS create pool/test, and now let's paste in this quick little line of code that I have here. That's just going to it's just going to touch a file and do a zpool sync. For those of you who don't know, zpool sync basically just makes sure that that your transaction groups are synced and that everything's out on data, so that you're sure that your data is safe. And here again, we've seen a crash. Now I wonder why that is. If we come here to dmessage, we don't have any information. That's not very helpful, and that can be pretty hard to kind of figure out what's going on. The interesting thing about problems like this is that, thank you, 10 minutes left. The interesting thing about problems like this is that you kind of usually, a lot of times what you will end up having to do is you will end up having to wait. And wait because in exactly 2 minutes, theoretically, the kernel will print out a stack trace of what is stuck. And that can usually help out a lot. But there's a slightly faster way to do it if you don't want to sit around and wait. And you can do that with this handy-dandy quick little, very long bash script, which is included at the end of this presentation, so that you can copy and paste it in. Basically, what this thing does is it just prints out all of the stack traces in the system and dedupes them so that you can see which ones may or may not be stuck. Now, a lot of times you will get some that are pretty standard, and especially if you scroll kind of to the bottom. And with ZFS, ZFS does spawn a whole bunch of task queues. So you will find a lot of threads which are normally just kind of stuck here like this, and they're just waiting for some work to do. So in this case, task queue thread, these are all just threads that are waiting for more work to do, and there's nothing really there. But if you scroll up and you look at the unique ones, here we can see that we're stuck in txt wait synced. Now, that's kind of interesting because usually the TXT sync wait sync usually a TXT sync should happen every 5 seconds or so. So there's no reason that this should have kind of needed to wait for it. Or I'm sorry, the zpool sync command is waiting for that to finish because that's like its entire job. But there's no reason that it really should have been stuck. Let's take a quick look. The only thing that I did before that was I touched a file. So let's go take a look at that code real quick. And we're going to search through the code for ZFS create, because that is the function that is responsible for creating a file. And we are going to search in the right directory and for the right kinds of files. So let's take a look around here. Here's the function, and let's see if we see anything suspicious in here. Because helpfully, I've been very nice in commenting all of my bugs that I've added. And this function does do a lot, but I think pretty soon. Whoa, okay. I'm just not ready for that kind of commitment. Okay, so what happened here, if you look at the code, is basically I commented out this line, which is dmutx commit. What this represents is effectively what's called a kernel deadlock. And basically, the way that this works is the zpool sync thread is waiting on some resource that will never come. And this can happen for a couple of different reasons. One of the big reasons that this can happen is basically because that thread is itself waiting on something else. So if we come back to the slide, if I can get to it. So basically, this picture right here, which has been helpfully provided by Wikipedia, because I didn't want to redraw it, basically, this kind of explains what a standard kernel deadlock looks like. And basically, the idea is that you have two threads, and each one of them is holding on to a resource and wants the other one, and they didn't ask for them in the same order. And so you have one thread that's holding resource A, or in this case, it says resource 1, and it is waiting for resource 2, but it can't get it because there's another thread which already owns it and is waiting for resource 1. So you end up in kind of this cycle of sadness where basically nobody can get access to the resources that they need in order to proceed. That's one kind of deadlock. Another one is the kind that we've encountered here. And basically, the way that this one is working is we simply have never given that resource back. We created a transaction, and we decided never to call commit on it or abort or anything else like that. And so the transaction has just ended up kind of stalled, and so that transaction is kind of lost in limbo. And so it will never be returned to the main sync thread. Let's just get rid of this, and we'll rebuild. Now, as before, in order to make this work, we need to reboot the operating system because basically the whole system, there's no real way to get yourself out of this kind of thing. But while we're waiting for it to reboot, basically let's just go over the symptoms that we kind of see here. Whenever you have a kernel lockup, it can be the result of one of a number of things. It could be a rogue call to sleep. It could be really simple like that, but it almost never is. It could be waiting on something else from a thread, like in this case, it was waiting on the TX commit. It could also just be waiting on. It could be waiting on a resource that is simply not really there or not available, or a signal that's not really going to ever come for some reason, either because it didn't listen in time and the signal was already issued before it was listening, or something else of that nature. So, okay, so we're back here. Let me quickly just get us rebuilt, and we will try one last time. So does anybody have any questions on that while this is rebuilding? Should just take a second. If I saved it. I believe I saved it. Yes, I did. Any questions? Okay. So now that we have that, let's do one last thing. And basically what that thing is let's try to create a bunch of files. Let's see what the I/O looks like if we try to write a whole bunch of data to, I guess in this case we'll just do one file. So I'm going to take my convenient little command right here. Now, for those of you who are not, super familiar with some of the things that I did here, basically all this is doing is it's going to write data as quickly as I can kind of muster to this file, which is pool/test/yes.txt. And first, let's create that data set again, because we still have not been able to yet. Pool/test. Oops, and I did that. Oh, this is what happened. Okay. So we're writing this data out, and I'm looking at the rate that this is getting written out, because the thing I'm kind of worried about here is performance. And it's really spiky, if you notice. Like, it started out real slow, and now it's going really fast. Now it's back to slow again. That's kind of weird. Usually in ZFS or any file system, or really any application that you'd write, you'd kind of expect it to have pretty even performance, especially for something like this where we're just writing data to a file. So let's go take a look. First thing I want to do is run htop, and that's kind of weird. For those of you who didn't kind of immediately see it, but basically we're writing data to a file, and what's interesting here is that we're using a whole lot of CPU. And you can see that in htop they helpfully color code this, so you can see that this is red CPU time, which means time stuck in the kernel. And if you look around at some of the options, you can go here to hide kernel threads and disable that. And you can see that we are using 84, a whole lot of percent, way more than you'd kind of expect for writing data in these ZWR ISS threads, which is kind of interesting. Now, that in itself, those threads kind of do a lot. Those are the threads that happen to do all of the kind of issuing I/O and calculations related to doing I/O and things like that. So let's do a little bit more analysis here. Earlier, I forget who showed it, but we saw what a flame graph was, and that's very helpful because now I don't really need to explain it. But basically, what a flame graph is, just as a quick recap, is it is kind of like a visualization of how much time your CPU is spent doing any given task. So let's restart this, and I'm just restarting it because I want to make sure that I get kind of the same picture again. So we'll just rm pool test yes.txt. And we will start again. So while we're doing that, I'm going to just paste in right here this code that I have. And again, this is all at the end of the presentation. But all it's going to do is it's going to take 10 seconds and wait and kind of take a picture of what that CPU was doing in those 10 seconds. Should be done in just a second. There we go. And let's go take a look. Come here. And it's not that control, it's this one. And it should be this guy right here. So this is what it was doing. You can see it spent about half of its time idle. That's what all this stuff is right here. And you can see that it says do idle. So that's kind of a good indication. But you can see here that the ZWR ISS threads, they're spending pretty much all of their time here in Zio checksum compute. That's interesting because usually in ZFS we use LZ4 checksumming, and that's pretty non-intrusive. It doesn't, it doesn't really take a whole lot of CPU to do that. So let's take a look at this. Let's cancel this and go back to here. And we will go to Zio checksum compute. Okay, right here. And, okay, this is immediately suspicious. Find out if anyone would notice if I started mining bitcoins here. Mine bitcoins for a bit every time we do a checksum. That would probably do it. So here we have this thing which is obviously eating up a whole lot of CPU right here. This is just a hard loop. Let's go see. Oh, so here's another interesting thing. Helpfully, I decided to dump the bitcoins to this ZFS debug message. And for those of you who are not familiar with this, this is also another really helpful thing for finding any issues that might be happening with ZFS. And that is, for those of you on Linux, it's available through proc spl kstat ZFS debug message. And as you can see, we found all kinds of bitcoins. So many bitcoins. Now, this is kind of a virtual file, so this is like an self-updating list that gets recycled kind of circularly. So this does not have everything in it all the time, but this can, and you can go through the whole thing, but as of 080, this is now enabled by default. So you should be able to always at least see these messages and get an idea of what's going on. Almost done. So performance issues. What do they look like? Basically, in general, it's just whenever somebody complains. It's whenever a process isn't moving as quickly as it should be, whenever it's using up more resources than it should be, or anything else. Whenever you're looking to debug something that's a performance problem and not just a hard crash or anything else like that, the important thing is basically to try to figure out what your bottleneck is first. It could be CPU, in which case the best things to check are top or htop. If it's RAM, you can also check top or htop and look at how much RAM it's using, or free-m. Disk I/O, you can check iostat-mx1 or iotop. Those are all really good tools. And for network, which doesn't so much happen probably for those of us here at this conference, but in general, you can look at iftop and get an idea of how quickly data is moving in and out over the network. It might also be waiting on another process, so possibly you might need to check for other slow processes that your process might depend on. When it comes to finding the culprit, the best tools that you can use are flame graphs, as we showed earlier, and another really good one is perf-top, which I'll show really quick. So we'll run this again, and then if I run perf-top, you can see kind of the same kind of information. It's a bit harder to see where the stack traces are, but this can give you a really good idea of what functions are really hot on your system and causing the most problems. In addition, in terms of memory bottlenecks, a lot of the time this will indicate some kind of memory leak. And if this does indicate some kind of memory leak, what I suggest you do is you can compile ZFS with the ZFS debug mem enable and SPL kmem debugging, I believe, are the two flags. They're kind of confusing, but they're documented in the configure script. And basically, when you turn them on, ZFS will enable some leak detection, which should tell you when memory has been allocated but not freed, or when it has been double freed. So these can help you out pretty enormously when trying to find memory leaks. Other than that, you can look at some of the proc files and try to figure out where all of this memory is being allocated to. Some of the ones, especially in Linux, have like procslab info can be very helpful when finding these problems. Finally, for disk bottlenecks, We have a ton of tools in ZFS being a file system, including zpool iostat, and you can add any number of flags. These were already kind of shown by Brian, to show what kinds of things they're capable of displaying. But basically, they can give you the latency, the size, and the queuing statistics of pretty much all the IOs in the system. You can add a -v if you're really crazy and want to see everything for every disk. The ARC stats can give you a good idea of what's going on with the ARC, how much memory it's using, and those kinds of things. And again, IOTop can be really helpful in just determining, especially how busy disks are, because they just give you a nice percentage number. For network bottlenecks, I don't have a whole lot to say here because I don't deal with these too much. But basically, usually, however much data you send over the network, the only thing you can do is either don't send it or compress it. And so you can, kind of try to address your problems like that. New tools that are coming out, there's BPF trace, which was mentioned before, and BPF trace is basically it can help you print information about kernel function calls. And the same thing with funcgraph. It's a kind of a similar utility, but it gives you like kind of the call hierarchy of everything. And finally, ZFS debug message. For resources, these are kind of all the things that I talked about, including this nice, really long bash one-liner that my coworker provided. And you can find all the rest of the stuff, just all of these other tools on GitHub, and use them as you see fit. Any questions?